So we have looked at interiors and closures of sets. Okay. Before looking at our next concept, let's look at an example. If I take rational numbers in R, okay, the interior, it doesn't contain any open set, is empty. That is an aside, but the more interesting point here is what is a closure? It's all of R. Remember, the closure consists of those points so that any neighborhood contains some point in Q. So that is, and every point has every neighborhood of that point contains a rational number. Okay. So that is basic properties of real numbers. So closure is all of R. Okay. So this means that you know if you know, say, a continuous function on R, you know it arbitrarily close to any point or anything else you know on R. So in this case, we'll say definition, we say A in X is dense if A bar equals X. Okay, so it's dense if A bar equals X. So this is an important notion, and having a dense set will become important. And we might as well make another definition. X is separable. This is a misleading name, but it's X is separable if X has a countable dense set. This is rather important in functional analysis, where things being separable lets you control things because you can control countable things. It won't be so important in this topology course, though it will play a role in a couple of places. Okay, so set is dense if it's everywhere. A less important definition we will make is of being nowhere dense, but first let me define definition. We have defined the interior of A. The exterior is kind of the opposite of A, but it's the largest open set which is disjoint from A. So that's going to be X minus A interior. But I could write it in another way. I could write it as X minus A bar. Okay, so so we have implicitly used the following proposition. Proposition is that X minus A, here it's better I write interior of X minus A, is actually X minus A bar. And the easiest way to see this, maybe this will illustrate it, is use the characterization in terms of maximality. Okay, so note we use characterization of interior of any set. Okay, so there were three conditions. First of all, well, I don't know if this was the order they were stated earlier, but first of all, you note X minus A bar is open as A bar is closed. Secondly, X minus A bar, well, A bar is contained in A, so this is contained in X minus A, where order gets reversed when we are taking the set difference. So this is contained in X minus A. That's the second condition we need. And the third condition is that suppose we want a maximality. Okay, so suppose V is contained in X minus A is open. What we have to show, we show that V is contained in the quantity X minus A bar. Okay. Now note that this is equivalent to saying that V intersection A bar is empty, because they are both subsets of A bar, which is equivalent to saying A bar is contained in X minus A. X minus V. Okay, but what do we know? So V is contained in X minus A. So this is again similarly equivalent to A is contained in X minus V. But what do we know about X minus V is closed? So we know X minus V is closed because V is open. Okay, so as A is contained in as A is contained in X minus V, and x minus v is closed. By definition or by the characterization of closed sets, A bar is also contained in x minus v. So any closed set that contains A is contains the closure. So x minus v is a closed set that contains A, so it also contains the closure. So this gives us proof that the interior of the complement is the complement of the interior. It also gave us an exercise in playing around with these definitions. Okay, so let me just make a definition here. This, as I said, is less important in being dense, but very important in one particular context. We say A in X is nowhere dense. Kind of the opposite of dense, but a typical set is neither nowhere dense nor is it dense. So it's an A in X is nowhere dense if the exterior of A is dense. Okay, so it's dense, and it's, in fact, you can say is a dense open set. So as an example, if I look at R inside R2, this is nowhere dense. Now, being dense and being nowhere dense are incompatible. You can think of an exact statement for this as an exercise. But a typical set is, like say, an interval in R is neither dense nor nowhere dense. It's dense somewhere. It's dense for part of it. So its closure is some set which occupies a certain amount of space, and its closure of its complement is also closure of the complement of its closure. Closure of the complement of its closure also occupies certain space but doesn't cover everything. Okay, another important definition. So we talked about interior points and closures. So exterior points. What happens to points that are neither in the exterior nor in the interior? They are called the frontier. It's like a country's borders. You're either inside the country, or you're completely outside, or you're on the border. But the frontier is also called the boundary. Frontier of A for A in X. Well, there are a couple of ways you can define it. A in X is defined as frontier of X, or frontier of A, is by definition, you look at the closure of A, those points that are in the closure of A, as well as closure of X minus A. Okay, so you can take it as an exercise. They are neither interior nor exterior points. So frontier of A is X minus interior of A union, well, I better spell this out as interior of X minus A. Okay, for symmetry, let me write this also as int of A. So you look at the points that are neither in the interior of A nor in the interior of its complement, nor in the interior of its complement. So let's take the exterior points. Look at the interior points, look at the exterior points. Frontier is neither interior nor exterior. Okay, this is more commonly called a boundary, but when you study geometric topology or algebraic topology, you will study manifolds with boundary, and the boundary there and the boundary here have entirely different meanings, even though they are capturing a similar geometric idea. And so there is endless confusion in statements, especially in exercises or exam questions, because of the mixture between the two terms. So best to think of this as a frontier. It's the set topology thing. The manifold boundary thing is the more geometric notion that we want. Okay, so now let's look at a set which is a bit different from these. Okay, so if I look at a set, well, its set could be some blob and a line here, but it could also have a few points like this. So these are what are called isolated points. Okay. So these are points which have neighborhoods which don't even have points of the same set. So these are isolated points in a set. Okay. So we can as well define A in X in a set is in a space is isolated if Well, I can say there exists an open set which intersects that only, but it's really just saying that if the set A is open, the single point is open. So these are isolated points. Okay. So you may think you can kind of throw these away and keep only non-isolated points, but you can, but then certain things happen sometimes in an interesting way. What I could have is I could have a sequence of points like this converging to this, and this is my whole space. So all these are isolated, but this one is not. Okay, so if I look at the set minus isolated points, this could have further isolated points. You can get rid of these, and then you could have further isolated points. And sometimes what happens is after finitely many steps, these vanishes. So you can call something like this a finite depth space in a sense. Okay, in foliations, there is a notion of a finite depth foliation, which is essentially this, but for a special class of spaces. So these are these isolated points. Now any other point in a set will be, which is not isolated, will be what's called a limit point. So you approach that, and these are like limit points you would see with sequences. So let's make a definition, but here we have a set point not necessarily in the set, so outer points could also be limit points. So given A, so fix A contained in X, so we say X in X is a limit point of A if for all V open such that X is in V, then what we have is there exists, so I can write it in terms of intersection, V intersection X, not X, A, the set A, minus the point itself is empty, is non-empty, I'm sorry. So we say something is a limit point of a set if given any neighborhood around that point. So if I have a set which maybe it consists of this line but does not have anything below, and then it has this, and it has a couple of few isolated points, then anything either this is a limit point here, this is also a limit point on the border, though it's not in the set, while these orange points are not limit points, even though they are in the set. And the idea is simple, that is to say we look at this gray circle, given a neighborhood of these, which is some small enough gray circle and these, okay. If every neighborhood around this point intersects A and in a point different from X itself, then we say that it's a limit point. Okay. Now here every neighborhood does intersect because it contains X, which is a point in A. Okay. And now you could be outside this set, but you could still be a limit point. Now if you recall the characterization of points in the closure, okay, so by our earlier characterization, we have the following proposition immediately. If X is a limit point, if little x is a limit point of X, or not of X, but of the set A, then X belongs to A bar. Okay. Why is that? Because we have proved. So I can as well write it down. If X is a limit point, A, then for all V in X, V open, if little x is in V, implies that V intersection A minus X is non-empty. But that of course implies that the bigger set is non-empty. V intersection A is non-empty. Okay, and this is true for all V. Okay, therefore X belongs to A bar. We had characterized closure points as being those where this happens. Okay. So let's note the following observation. A set A in X is closed if and only if A contains all its limit points. Okay. So one way is clear. If A is closed, then A is A bar. In fact, this is a characterization of being closed, because A bar is the smallest set containing, closed set containing A, and if A itself is closed, then A bar has to be A itself. And conversely, if A bar is A, we know A bar is closed. It's a closure is the intersection of closed sets, so it's closed, and so A equals A bar. Okay, and so we have seen that every limit point of A is in A bar, hence A. Okay. Now conversely, what do we know? If A contains all its limit points, we show A equals A bar. Okay. Now, so suppose X belongs to A bar minus A. So this is of course for contradiction. We'll contradict it. Then what do we know? We know that for all V open, by our characterization of closure, if for all V open in this total space X such that little x belongs to V, given any open set which contains V, A bar intersection V is non-empty. Okay, so I'm sorry, that's A intersection V. This is the definition of a limit point, that the set intersects every neighborhood of this point. Okay, but X does not belong to A. So let's look back at the definition of a limit point. A limit point of A said that A minus X. So A minus X, if I remove X, X is not here, is A. So A minus X intersection V is empty, is non-empty. This is what we wanted to show. So thus X is a limit point. So all this is kind of uncovering the structure in terms of density and so on of the set. So let's make another definition here. A space X is dense in itself. Well, that doesn't mean X bar is X, which is true by definition, if every point of X is a limit point. Okay. So this is saying that if I take any point, so that is equivalent. That is, equivalently, X has no isolated points. Now in this context, the example that I mentioned earlier should become a bit clearer. So dense in itself sets are nice, and if you add in certain other properties, they almost get characterized. Okay, in special cases, okay, if they're totally disconnected, as we will see, and they're dense in itself, they get characterized nicely. So you want to sometimes make a set dense in itself. Well, you could throw away isolated points, but as we saw in the previous example, you could have the set. Let me be a little bit concrete here. If I looked at example, if I looked at the set X, which is 0 union 1 over n, where n is greater than or equal to 1, which is a positive integer. Okay, so then 0 is not isolated in X, but everything else is. So we can look past to the limit set, that is, we will pass to the set of limit points, and that set will be exactly one point, which is 0. But now if I pass to the set of limit points or the set of limit points, they just vanish. Okay, so there is a relatively easy proposition that limit points of limit points will not create new points, but points can get destroyed in this if we are looking at throwing away isolated points. So when we want to pass, and of course you can think about this and construct n-dimensional or infinite dimensional or any cardinality examples. When we want to try to construct a dense in itself core of a set, we have to throw away isolated points. This may create new isolated points and so on, and then we will get a sequence, maybe even more than a sequence. You have to intersect some collection and get a dense in itself set, which could of course be empty. Okay, so these were some of the notions we saw of density, limits, etc., which will give you some sense of the structure of topological spaces.